Hello, everyone, and welcome to the webinar series offered by University Transportation Center for Underground Transportation Infrastructure. My name is Reza Hedayat, and I'm a faculty member in the Department of Civil and Environmental Engineering at the Colorado School of Mines. I'd like to welcome you all to this webinar series. Here, UTC-UTI is a transportation center that's essentially a collaborative effort between Colorado School of Mines, Lehigh University, and California State University in Los Angeles, and our mission is to address the FAST Act priority area of improving the durability and extending the life of the transportation infrastructure. In this webinar, we have 3 presentations offered by the members of the Transportation Center with the general team of Intelligent Systems for Transportation Tunnel Analysis, Design, and Monitoring. Each presentation will run for 30 minutes, and that includes 25 minutes of presentation time and 5 minutes for questions and answers. And I'd like to encourage you all to use the Q&A option at the bottom of your Zoom panel to share with us the questions that you may have for the speakers, as they will have a chance to either see your questions during the talk or certainly during the question and answer time period to address the questions. During the presentations, we will have the attendees on the mute option, but then when the question and answer time comes, the attendees will be unmuted to share the questions with the panel members. So the first presentation is offered by my colleague, Dr. Marty Gutierrez, and I'd like to introduce him and then invite him to share the presentation that he has. So Dr. Gutierrez is the James Padden Distinguished Professor in the Department of Civil and Environmental Engineering at Colorado School of Mines, and also the director for the University Transportation Center for Underground Transportation Infrastructure. Dr. Gutierrez formerly had the postdoctoral fellow, senior engineer, and program leader positions at the Norwegian Geotechnical Institute, and also was the associate professor and then later full professor at Virginia Tech. He has held visiting professorship and research positions in China, Chile, France, Japan, South Korea, and the United Arab Emirates. He was the founding chair of the Department of Civil Infrastructure and Environmental Engineering at Khalifa University in United Arab Emirates. Dr. Gutierrez has published more than 300 papers in book chapters, journals, and conference proceedings, and has given keynote and invited lectures in a number of conferences, and has been responsible for more than $20 million in research funding. So with that, I'd like to invite Dr. Gutierrez to go ahead and share his screen.
Thank you for the introduction, and good afternoon, everybody. And thank you all for joining this webinar by the University Transportation Center for Underground Transportation Infrastructure, which is a Tier 1 University Transportation Center funded by the Department of Transportation. In line with the theme of the webinar today, I'll be talking about back analysis of tunnel response from field measurements. Background and motivation. I'll be talking about back analysis. And what is back analysis? Other terminologies for it are inverse analysis or parameter identification. And it requires the determination of input parameters in computational model using field monitoring data. The back analysis is particularly suited to underground constructions like tunneling, because when we tunnel, we learn more about the ground conditions and the geology and the response. And as the construction progresses, we are able to uncover more information. But despite the ability of data from field monitoring, they are, however, rarely carried out into technical practice. Well, the challenge for back analysis is to develop an algorithm to find a set of input parameters that will minimize excuse me, the difference between predicted and measured response. Excuse me. So we need to be able to match the numerical predictions, computational predictions with field performance by adjusting the input parameters. Okay, Let me differentiate between forward and back analysis. In forward analysis, we have a set of input parameters. We do then our forward computational model, which is what we usually and typically do. And then using the computational model, we predict a response. And most of the time, that's it. We have a prediction, and we hope that it's the correct prediction. Most of the time, however, the predicted response do not correspond or do not agree with the field measurements. And that is where back analysis comes from. In back analysis, we have the reverse, we have the observed response, and we have to develop an inverse computational model to try to predict or to try to determine what are the input parameters that will match the observed response. The most rigorous approach to do back analysis is by the so-called gradient methods. That is, we try to get the slope of the response at a certain time. And we use the slope to move forward and to make an improvement on the predicted parameters. So if pk are the set of parameters, or the vectors of parameters, delta pk is the change within an iterative step to try to improve the prediction, and pk plus 1 is the improved set. We could do this by the so-called sensitivity matrix A, and we have to get the inverse of that. The sensitivity matrix A is nothing more than the gradient of the difference between the prediction and the measurements. We try to minimize this. This is the so-called error, difference between prediction and measurements. Try to get the gradient of that with respect to the parameter vector P, and that's what we call the A. In finite element method, we have the stiffness matrix, we have the deformations, and we have the loads. K is the stiffness matrix, F is the load vector. This is a typical finite element formulation. The challenge is to find the so-called sensitivity matrix. A is defined as the inverse of K and the derivative of K with respect to C divided by Z, which is our displacement vectors in displacement vectors in this case. This is very difficult to derive most of the time to establish this sensitivity matrix. But even if we could, there are many issues with the so-called gradient methods. Let's try this. This is a synthetic back analysis problem. It's a axisymmetric finite element model of a circular tunnel. We model only a quarter section of it. And we try to do a forward model and predict the deformation. And then we pretend we don't know the parameters that led us to the predictions, and we try to predict it using back analysis. Here, there are only two parameters that are involved: the Young's modulus and the far-field isotropic far-field stresses P sub O. So we do a back analysis, and you can see that the gradient method, only after about 10, 12 iterations, get into a very good estimate of the Young's modulus and the far-field stresses, and also the objective function, which is the least square difference between predictions and measurements, goes down to 0. So it's very efficient. But remember again, this is a two parameter elastic problem. So two parameter elastic problem, and it forms very well. The moment you have more than two parameters, in this case, we have 4 parameters: the Young's modulus, Poisson's ratio, and the far-field stresses, and we now have anisotropic stresses. You can see that the trend towards the final parameter is no longer simply monotonic. There's some cycles, it goes up and down. It really struggles to get to the true solution. And more or less, the only reason this method used is that we combine the gradient method with some search. We try to search for the parameter at the same time. So in paper, it's very good. And when we were doing a study of this, we found out that almost all papers that use the gradient methods that you find in the literature work only use as an example 2 parameters to back analyze and an elastic problem. And we found it to be odd. Why is it everybody's doing only two parameters elastic problem. It turns out that this only works for those cases. If you have nonlinear problems, it doesn't work. If you have more than two parameters, it barely is functioning. So in theory is very good, but in practice, it doesn't work. So an alternative to so-called gradient methods is the so-called heuristic back analysis. This is nothing more than doing a search. You have vectors of the different parameters that are involved. You try to get the minimum and the maximum, and you discretize the space between the minimum and the maximum of the different parameters, and you try to do a search of which of those combination of parameters will provide you with the best estimate. It's nothing more than a search procedure. You still solve the problem directly using a forward model. As in forward modeling, you just try different sets of parameters until finally you succeed. How to carry out those searches is a challenge. And then here we could use the so-called heuristic methods. Heuristic methods are experience-based for problem solving, learning, and discovery. We do not guarantee the solution to be optimal, to be very, very rigorously optimal, but the set of parameters are good enough. It uses search trees, okay? So instead of generating possible solution paths, it looks branches that are more likely to produce outcomes, and those are the ones that are selected. It's an iterative search. It searches on the different parameters and it follows path and avoids unnecessary paths by assessing how close the current iteration is the solution. It's a viable technique for difficult optimization problem. This back analysis is really an optimization problem or least square optimization problem where you try to limit the difference between prediction and measurements. So, and it exploits randomness in the system to try to get to the solution. Examples are neural networks, simulated annealing, genetic algorithm, and evolutionary algorithms. Here we develop two methods. One is the simulated annealing. I'm not gonna go to give you the details, the mathematical details, but simulated annealing process follows a physical process, which is how we create a metal with very good properties. It simulates the annealing process of metals. How we come up with a very optimal atomic structure of a cooled steel, for example, or other metals. So it uses a so-called a cooling procedure until we arrive at a theoretically perfect crystalline structure in the material. It uses minimizes the number of imperfections and dislocations. And then during the cooling, it follows its own optimization path. So we have a so-called program that uses the temperature. The temperature here is nothing more than a fictitious parameter to try to order the search and then allow the search to converge into the best solution. This is a problem of a deep tunnel. We only model half because it's symmetrical. And we have 4 parameters to back analyze: the modulus, ratio of horizontal to vertical stress, the cohesion, and the friction angle. And you see that after a certain number of steps, we arrive at the back calculated parameters that are very, very close to the one that we use to generate the model. And here is how it behaves. These are the 4 parameters that are being searched. As you can see, the elastic modulus tend to oscillate around the true solution, oscillate around the true solution, friction angle as well. But this is not how we judge how it moves with the parameter converges. Although the parameters tend to converge between the maximum and the minimum, what determines the convergence is the criterion, the error function, the objective function that we use, and you can see how the objective functions, despite all the oscillations, try to converge to 0 and achieve an optima. The other back analysis procedure that we use is the differential evolution algorithm. And this is based on the theory of survival of the fittest that we have in the theory of evolution. The fetus vectors, these are so-called those that optimize the functions, lend their genes to the offspring. And the differential evolution algorithm bypasses the requirement of binary system in genetic algorithm and makes it more user-friendly, because genetic algorithm used to be only for binary systems, but we can bypass that with the differential evolution algorithm. Degas-like simulated listings are direct search methods. And again, the same problem as before. We even have, interestingly here, we installed an MPBX at the top of the tunnel, different points, and we also have inclinometers, and you can see the predictions between inclinometer and the history match or the back analyzed response are matching very well. So the program, the algorithm works very well in getting the parameter. This is how it works. First, we start with the random initial distribution of parameters. This is the probability distribution functions of the parameter at the beginning. Okay, so different, this is the Young's modulus, K0, cohesion, and friction angle. So from the most realistic minimum to the most realistic maximum, it could have, for example, a Gaussian distribution or a random distribution. And what the differential evolution genetic algorithm does is to narrow distribution, to narrow this. You see the distribution getting narrower and narrower to the point that we have gotten the true value. So these are the lessons that we use in these two methods. By the way, we have implemented this method in Flock, and there are fish functions that implement the search process for the back analysis. And they're rather involved to program, but they are quite easy to use and quite easy to implement compared to other methods. The advantages of these methods is they're not greedy. They don't get stuck in a local optimum. Like, for example, the gradient method, you can get stuck in the local optimum, which is not the global optimum, okay? They allow for uphill movements. You can jolt the system. The system can be jolted to get unstuck out of local optima and then continue until it finds the true optima. You can make independent assumptions on the initial parameters, what they are, how they're different. The overall equation that you're solving need not be continuous. You don't need the gradient of the parameter of the response with respect to the parameter. Independent of convexity status, you can have a very nonlinear problem with very irregular convexity characteristics. You can use it with heterogeneous data, different sets of data. You can mix stress, displacement, strain, loads, boundary loads. You can mix all of this. Unlike in the gradient method, that the only variable that you can solve directly is displacement. You can use relative deformations. For example, you can have the difference between the deformation between 2 points instead of absolute values. The history of the solution, if suddenly you have to stop, can give you a very good indication of what the local optima are. So, because you're always getting closer and closer. You can constrain the parameter. It shows very good efficiency and convergence. We apply this to demonstrate how it works. We apply this with the real problem of a tunnel in China. This is a tunnel that's 450 meters long from Fuzhou to the airport. And this is a well-documented case. There are so many instrumentations that's been done, subsidence, MPBX, forces, convergence, etc., etc. So this is the geology. So we try to apply the back analysis on this section. This is the tunnel construction. This is the left tunnel, the right tunnel. This is the sequence of excavation. What is nice about this is that we can use the measured response at the earlier stages of the construction. So it starts this, the first stage is this one. close to the crown line. Second two, then you have the crown, and then you have the bench. So you could use this earlier response, which is monitored in the tunnel, to predict how the right tunnel is going to behave. The tunnel is four-fold with the rack bolts. And these are the field monitoring. These are the instrumentations. There are subsidence measurements on the ground surface at different points, 8 locations. There are MPBX installed at the top and inclined on the left and the right boundaries. And there's been a very good history of the measurements of the subsidence, and of course with the development of the displacements, the different points in the instrumentation with time. This is the FLAC model of the problem. We have a refined mesh close to the tunnel and a very coarse mesh around the tunnel. Those are the different co-excavation stages. We model the rack bolt with an equilibrium continuum. We homogenize the rack bolt and the rack close around it. Okay, here are the different drips. Okay, and the different excavation stages and the different instrumentations. We match 2 instrumentations: the subsidence and the measurements at the MPBX, and we are able to match. For the left tunnel, the subsidence, okay, both the left and the right tunnel. I'll talk about how we carry out the left and the right differently. These are the center lines. And you see a good match between the predicted and the measured subsidence. This is the comparison of the back analysis. This is still back analysis of the MPBX displacements along the MPBXs on the left tunnel, and you can see very good match between the left and the right tunnel. We were then, this is again the back analysis responses. We were then able to arrive at this set of parameters through back analysis. Now, using these parameters, we then predicted the response of the left and the right tunnel after the right tunnel has been excavated, because the left tunnel will also respond due to the excavation of the right tunnel. And you can see that there's a good match. This is now forward modeling, okay? We did the back analysis of the left tunnel, then we did the back analysis of both the forward modeling of both the left and the right tunnel using the parameters determined from the left tunnel. And we did get quite reasonable response, good matches in the subsidence. And then this shows you the displacement. And importantly, to show you the plastic zones. There's a plastic response in the tunnel to show you that the method works not only in the case of elastic response, but also in elastoplastic displacements. So in conclusions, gradient-based method, back analysis method look good in practice, but they are actually difficult to use. They look good in theory. Theoretically, they're very good, but they're actually difficult to use in practice. Like Yogi Berra said, in theory, there's no difference between theory and practice. In practice, there is. So when you apply all these theoretical things in practice, they don't actually work. So be careful. On the other hand, heuristic methods are found to be very viable techniques in the analysis of, in the back analysis of tunnel response, because they have very good characteristics. They're not greedy. They can unstack themselves out of a local optima, independent of initial variables. They're suitable for non-continuous, non-differentiable, non-convex problems. Can be used with heterogeneous measuring data, that is, you mix displacements, stresses, loads, etc. You can have relative value, that is relative displacements, for example, between 2 points, and you can constrain the parameter if you want. One thing we have to remember that when we do back analysis, we need to account for errors and delays in measurements, and those are typically difficult to account for. And back analysis remains a very challenging problem, but once we develop it and becomes really a viable tool, I think the industry could benefit a lot from using back analysis. I'd like to acknowledge my former PhD student, Dr. Batakos, whose work has been used a lot in this presentation. I'll be very happy to answer any question if there are questions from the participants. I think I got a couple more minutes.
Yes, thank you, Dr. Gutierrez. Now we have the time for questions from the participants. I do have one question, if I may ask. I would be curious to know if a similar method can also be applied for the case of underground or residential excavation systems or supports of excavation, when we have like a retaining structure that the neighboring soil formation would be deforming. Have you seen, or do you see similar type of application for this method for the support of excavation type applications?
I think we could. The method is general enough, and it's independent of the type of problem that's being used. We haven't tried it, but I'm confident that we could apply it for such cases.
Hi, my name is Parsa Haidarpur. I received my PhD from George Washington University, and right now we are working on multiple tunnel projects in DC metro area. I have a question for you. That would be, most of the times we have a soil layer, and there are multiple different layers that consists, and what we are basically encounter with. How would that impact the model? And the other one would be, I do a lot of construction impact assessment analyses, and what I'm really interested in is the displacements and how this method is good for, and how accurate it is in predicting displacements. Thank you.
Okay, the first question is with regards to geology. The method is not designed to predict changes in geology. Not yet, we're doing that. The method, in the example that I showed you, the method worked particularly well because it's a layered system, horizontally layered system. That is, the geology in the left tunnel is the same as the geology in the right tunnel. So the learn in the right left tunnel could be applied directly to the right channel because the rock types and everything are the same. But I think it's possible to account for changes in geology if you do this almost real time during the excavation. So during the excavation, if you find there's a change in geology, by all means, you should try to change the geology in your numerical model to adapt the geology to make a better prediction. In that case, you are probably one excavation stage behind in your prediction. That is still an improvement because in typical numerical modeling, you assume one geology, one input from the very beginning, and you don't try to change it no matter what during the process, and assume that the predictions are as good as what they can be, which they never are. So the advantage of the method is that when you have very initial data, you can try to improve it, because normally we don't try to get as much samples, and we don't do much sampling and testing to check along the length of the tunnel. So the best way is to try to adapt as you move along. With regards to displacements, actually the best predictions that could be made by the model are displacements, because they are the direct quantities. They are the easiest and the most accurate to predict. So yeah, displacements are actually the best, but most of the time we have other parameters that we try to predict. So, and the method could work with that in that case as well. Okay, okay. There's a question from Mr. Namli. How long did it take for you to make this back analysis? For the problems that I showed you, it took 2 days. 1 day for the back analysis and another day for the forward analysis in terms of computational time. And this was some time ago. I think you could do the whole thing in a whole day with faster computers that we have today.
All right. Thank you, Dr. Gutierrez, for the presentation. Next speakers are Dr. Mohammad Pourhomayoun and Research Associate Kabir Nagrecha. Dr. Pourhomayoun is an assistant professor of computer science at Cal State LA. Before joining Cal State LA, he was a technical project manager and senior data scientist at Vanda Incorporated, working on big data analytics for healthcare applications, large-scale machine learning techniques for risk prediction, predictive analytics, and data-driven approaches for healthcare. At the same time, he was also a visiting research scientist at UCLA. He's now the founder and director of the AI and Data Science Research Lab at Cal State LA. Kabir Nagrecha is the research associate at Cal State LA. His primary research focuses on AI and machine learning applications in various fields. In the past, he has worked on Dermalogica LLC on facial analysis applications, and before that, he worked with the Aerospace Corporation on autonomous vehicle control. He has worked with Dr. Pourhomayoun for the last 2 years on the application of machine learning techniques to problems related to underground infrastructure. So with that, Dr. Pourhomayoun and Kabir, please go ahead and share your screen.
Okay, hello everyone. I hope you are all healthy and safe in these stressful days. The topic that we are going to talk about today is using artificial intelligence, to be more accurate, artificial neural networks for predicting the operational performance of TBM, tunnel boring machine. So I'm going to talk a little bit shortly, briefly, and 1 minute introduction about the idea of the project, and then Kabir will continue with more details. He will share his screen and continue more details. So the idea is that, so the problem that we have with TBM is that it runs pretty much blind. So if the TBM machine does not have any idea about what's going on next. Okay, so yeah, there are some techniques, for example, using boreholes in advance to get some idea about the type of the soil or the soil composition in advance, but there is no technique, no advanced technique that can detect and predict for example, soil composition and consequently the operational performance of the TBM in real time. So that is why we use our neural networks, artificial neural networks, to make this prediction, and it can significantly improve the performance of TBM. And the reason that we are able to do that is that artificial neural networks are, of course, types of machine learning models that learn from historical data. So although there is a very high level of randomness in the soil composition, for example, but it's not completely random. There are still some pattern in the data. There's still some pattern in that soil composition, and consequently on the sensor outcomes and operational performance of the machine that we can learn by time. And then over time, if we can learn it from past data and then use it for predicting those values in future, this can significantly help the performance of the TBM. So this is the main idea of the project, and we use that. So we design and develop some systems. Kabir is going to talk about more technical details, and we use that for on some real data, on actual data from several tunnels in the Los Angeles and Seattle area. So Kabir, please go ahead and share your screen and take it away.
Hi everyone, can you see my screen?
Yes.
Okay. So today I'm going to be going through our research on the topic of applying recurrent neural networks to try and predict the sensor readings of a tunnel boring machine. So I'm going to begin by giving a bit of a high-level overview of the problem and the environment in which our proposed solution would be implemented. Now, our project is focused on tunnel boring machines, or TBMs for short. TBMs are one of the single most important tools in modern underground infrastructure development. They're used for large-scale excavation and construction all over the world. I'll get into some more details on the details of their operation in a minute, but let's just take a moment to see the consequences of their widespread use and popularity. Because they're used all over the world, they're also used in a variety of soil conditions. Therefore, they have to be adaptable to different environments, and any tools or systems developed for them should ideally also be applicable in a wide variety of environments. Developing tools and systems to aid TBM excavation and construction is also a high importance research area, simply because of how integral TBMs are to underground infrastructure. So let me get into a little bit more detail on the nature of TBM operation. The TBM is composed of a shield or tunnel support mechanism and systems for excavation and construction. The whole idea is the TBM will drill forward using the cutter head, and every few meters it'll place a precast concrete tunnel segment, thus combining the excavation and construction phases. This is a rather effective and efficient method, which contributes to their popularity. Now, just looking at this diagram, you may notice a slight issue, which was mentioned earlier. The operators of the machine cannot see past the cutter head, or, for that matter, around the TBM. This blindness tends to be an issue, and that's the problem we're trying to solve here. While TBMs are generally well optimized for their task, they aren't running at maximum effectiveness so long as they're running blind. They lack contextual information on their environment, and with that information, they would be able to be run more efficiently. There has been past research on this problem as it's an acknowledged issue. So let's take a look at some of the previous work done in this field to try and resolve the issue. Some of the previously proposed solutions involve attaching front-facing sensors to the TBM to analyze the oncoming rock face and soil. You'll see in the image I have here, this is the result of one of those approaches. The Institute for Subsurface Engineering Geodata Group had developed a front-facing sensor to be attached to the front of the TBM, and this is what the results looked like as the machine was drilling forward. Now, while the solution does have merit, it is rather expensive and does not fit into the existing infrastructure. It would require an actual modification to existing TBMs, rather than working within the system we already have. Now, there have been attempts to work within this existing framework by using the data that's already being generated by TBM sensors and mechanical data to try and predict how the TBM will operate, predicting its rate of advance, predicting how the TBM will react to the oncoming soil, prescribing parameters for the operator to set, and other important features that the operator needs to have knowledge on. And some other systems even try and predict the actual soil composition given TBM response or past soil conditions. Now, the thing is, these solutions have generally been implemented with more traditional statistical techniques. So while they have met with success, they tend to be limited in their adaptability or scope. For example, some solutions inherently are limited to working only in specific environments which are ideal for the setup. They aren't generalized to adapt based on input type. Alternatively, some systems require deep analysis of the existing worksite, such as the borehole method, which in and of itself represents a heavy time-based investment to evaluate the soil conditions and environment. So here's our proposed solution to try and address these issues: a deep learning-based system. Deep learning systems tend to be flexible, and the framework we're using is very generalized so that it can adapt to the available data and adjust its predictions. This flexibility and adaptability mean that the overall system can be applied to any environment with sufficient data being provided by the TBM. The fundamental approach is consistent regardless of location. This flexibility also applies to what we can predict. The nature of the system is that it's easy to set it up to predict any chosen sensor output, depending on the needs of the worksite and the operators. Now, the specific proposed deep learning system, the recurrent neural network. I'll get into further detail on this later, But for now, I'll say that one of the advantages of using this system is that it can provide continuous predictions on what's going to happen in the future. That is to say, the predictions will be continuous, not a matter of gathering data, analyzing, then moving forward and repeating. Instead, the system can provide predictions even as the machine moves and gathers data, as the recurrent neural network would be continuously fed the data and continuously make predictions. That'll be made more clear in a few slides when I describe the structure and function of the neural network. Now, there's another advantage of using deep learning. Earlier, I mentioned that the fundamental approach, fundamental structure of the network would remain the same regardless of where we're applying the system. Well, that provides a unique opportunity we can exploit. So this network, normally we would have to retrain it at each worksite. Though the structure is the same, we have to give it data from the worksite it's operating on. It has to learn the data from that worksite before it can reach maximum effectiveness. But what if two worksites were similar in their composition, say in a parallel tunneling project? Then we could transfer the learning that the system is done in one worksite to the other. That's part of the problem we tried to address here and something that we did test here. I'll go into further depth on the outcomes and the nature of this transference of learning in a bit. The data we're using in this project was provided courtesy of the LA Metro. A big thanks to them for providing the dataset. The data is from the new LA Metro Gold Line connector, a pair of 1.9-mile tunnels running in parallel. The project is budgeted at $1.7 billion and it's forecasted to be available for public use in 2022. This dataset is fortunately quite good for testing our proposed solutions. The data is collected at quite a high frequency, meaning that we can train our network on a rich corpus of information. The parallel tunnel system also allows us to test the aforementioned possibility of transferring learning from one tunnel to the other. Now, let's get into the actual details of this, the structure of the network, how the system is working, how we're formatting and cleaning the data, and most importantly, the results. I'll start with a look at our chosen system, the neural network. All right, so in a neural network, which is the machine learning system we're using, we essentially have a vast number of neurons or decision units working together. Each neuron receives a set of inputs, operates on them based on its weight, and gives some results. These results are fed to other neurons via these connections, and ultimately, all of the different decisions come together to produce some output. To train the model, we give it an example input, let it run all its operations, take the output and compare it with the label or truth for that example. Then, using the gradient vector with respect to all of the weights of the old neurons composing the decision, we propagate back the proposed change given by the gradient to minimize that error. Now, the details here aren't of quite such relevance, but what I want to make clear here is the importance of setting up the data and label associations so that the model can learn to connect the data and the proposed label. What I also want to make clear is the nature of the training, the stored weights on the neurons. Those two things together will be very important in understanding the nature of the transfer learning that we're trying to use here. I mentioned earlier that we're using a recurrent neural network. What separates the regular artificial neural network from the recurrent neural network is the recurrent layer you can see in the top left diagram. The idea here is that the outputs from previous input may be relevant to the new input. That is to say, what if the past affects the future? You see how in the diagram the recurrent layer is self-feeding. The output it gave for a past input, a past time step as it were, will be fed in to affect the output for the current input, the current time step. You see how this might be useful in a tunneling application where the previous sensor outputs are certainly extremely relevant and can be used to predict future sensor outputs. In this manner, we give it the past 3, 4 time steps and allow it to predict the next time step. Because the future is determined by the past here, we're able to give it previous inputs, previous sensor readings, and have the output be the future sensor readings. In the bottom left corner, I have a diagram of the actual neurons themselves. The most important thing to notice here is the reset function part. The idea behind that is that certain parts of the previous data will no longer be relevant. say data from 10,000 meters prior, will no longer be as relevant as something simply 1 meter ago. Therefore, the reset function will allow us to forget some of that information, so it's no longer contributing to our input. So what I'm going to do now is discuss how we're packaging the data to allow this function to work. Essentially, the critical part here is to include the last several time steps, so the output is dependent on the previous inputs. If you see the diagram here, across the top axis, we have our predicted features and the features that we're inputting. Those are the sensor readings and the sensor we're trying to find. I ought to note that although in this picture, I may give the impression that there's only a single feature being predicted, in reality, extending that to predict multiple features would be quite simple, simply a matter of adjusting the expected output. Now across the z-axis, we notice that we are feeding in many samples and receiving the same number of predictions. Every example input has an associated output by which we judge the machine's performance. Here's where it gets a bit tricky. Across the y-axis, you'll notice that the input is the sensor readings of the past several time steps. You'll notice across this axis, the time axis, we have times t-1, t-2, t-3. This represents the reading from the previous second, 2 seconds, 3 seconds ago. While I did say seconds there, it's not necessarily in terms of seconds. The idea is to simply have a consistent unit of time. Essentially, each of these time steps is representing data from further and further back in the past. Now together, we use this data to predict time step t, or the future time. You'll notice that no data is provided from time step t. Since it's from the future, the machine doesn't have access to that data yet, so we don't allow the model to use that data in predicting the sensor. It only operates on t-1 and further back, previous times, to predict future times. To go into some more detail on the nature of the provided data, we were only working with mechanical sensor data. Unfortunately, we did not have geological data to work with, so the machine was aiming to predict future sensor outputs based solely on past sensor outputs. The inclusion of geological data would doubtless improve accuracy by providing more information. No doubt you are wondering how we handle directly correlated features. Many sensor outputs are directly related to each other. Now, this is not an inherent issue here, as we're aiming to predict future time steps. So any direct correlations would only apply at previous time steps, as no data whatsoever is being provided from the predicted time. However, even so, we did eliminate directly correlated features that the machine was providing. For example, if the machine was providing information on advance rate and also machine speed, clearly those two things are directly related to one another. So when predicting advance rate, we wouldn't include machine speed as a feature, and vice versa. To reiterate though, the inclusion of these features would not present an issue in the evaluation of the experiment. Since we're predicting a future time step, previous direct correlations would not be applicable to the future. So in a real-world use case scenario, it would be fair to include all sensor outputs as inputs to the system. Getting to some of the more practical details of the dataset, some of the sensory outputs were not being outputted at the same rate as others. Therefore, to find a common baseline so that each feature was being found at the same rate, we resampled the data to a rate of 1 feature every 10 seconds. What that means is that when predicting sensor outputs, we're predicting sensor outputs 10 seconds in the future, using data from the present t-1, data 10 seconds stale, t-2, and data 20 seconds stale, t-3. I mentioned earlier that we had the data for parallel tunnel systems, 2 tunnels. Each tunnel's data represented several days worth of active tunneling time, and the total excavation time would be across several months. Now, on to the results. Here we see 3 selected features and the predicted results of the system in blue versus the reality of what occurred at that time step in orange. Below are the root mean squared errors for each feature. As is evident, the system does indeed predict the results well to quite a degree of accuracy. A degree that means the results would be quite useful in predicting sensor outputs. Now, let's consider the point I brought up earlier, the possibility of transfer learning. Earlier, I described the system wherein the network weights are adjusted by feeding the network various training samples. The theory here is that if we were to train the network on data from one tunnel in certain geological conditions, then those weights can be reapplied to another tunnel in similar geological conditions. Here's what the results look like. Now, I just want to note, so this isn't misleading, these results are generated by the weights of the first tunnel, retrained on about 15% of the second tunnel, and testing on the rest of the second tunnel. The point here is to show that even with light retraining, only 15%, we are able to produce results comparable to the full training set results displayed earlier. By virtue of utilizing the weights of the first tunnel. I'd also like to consider the limitations of the transfer learning approach. In our tests, we only tested this on parallel tunnel systems. Therefore, the ground conditions for the TBM in both tunnels was rather similar. It is possible that this approach would also work across varying ground conditions, but that is something we have left for future investigation. One possibility is that the inclusion of geological data may assist in that approach, as the machine would now have information to be able to adjust to both systems. With that, I'd like to bring my presentation towards a close and give a big thanks to the UTC for the funding and support, and also the LA Metro for providing the used data. I think I have about 5 minutes, so if there are any questions, I'd be happy to answer.
Thank you, Kabir. So we welcome any questions. Seems like there is one question on the question and answer box. How many data set did you use in learning step, and what was your input data?
So when you say in the learning step, how much data do we use? Well, normally we were using about 70% of the provided data, which translated to about, I want to say around 20,000 samples. And then you're saying the input data, we are using entirely mechanical sensor data. So what I mean by that is the data that the machine is recording on its own functions. Like here we have advanced speed, articulation force, thrust force. We would also have things like cutter head speed, cutter head rotation speed, force injection, foam injection ratio, basically all of the mechanical sensor data. We did not have geological data information on the soil. Everything else was fair game for the machine.
Okay. And a follow-up question, how do you configure hidden layers from the same person who asked the earlier question?
Right, so we're using a recurrent neural network here. So essentially the idea here is that we just have several recurrent layers in between the input layers and the output layers. And the training would adjust the weights in these layers of the neurons in these layers to be able to better understand how to manage the past inputs and the future inputs. Now, for the configuration of the hidden layers, we did make the decision to use GRU units, as I have in this diagram, instead of LSTM units. The idea here is that while we did have quite a rich data set, LSTMs do require more training to achieve accuracy than GRU units, and they're generally used to model more complex relationships. Therefore, we thought that the GRU unit would be more appropriate for this situation. So that's the general idea behind the decisions we made in configuring this system.
Okay. There's another question. Is there a way to incorporate engineering experience or expertise into this approach for better prediction?
I mean, absolutely. I think that with more expertise in terms of understanding the TBM, understanding the necessary sensors, understanding the relations between sensors, we would be able to perhaps pre-train it or perhaps select the features in such a way that it would be better adjusted to learn better, to start from a better base. And perhaps then it could learn quicker, it could learn more accurately, and overall it could produce better results in this way.
Okay. And I think we can maybe attempt a few more because more questions are coming in. Mm-hmm. There is a question, if you assume that the prediction of values shall give reliable results, wouldn't this be true that it only works in homogeneous geology? As soon as something unexpected happens to the machine, for example, change in geology, the approach would not work as well?
Oh, yes, absolutely. That's why I did mention that if we had the geological data included, the accuracy would likely be higher than it currently is. Because, as you mentioned, unexpected changes in the geology, since the machine doesn't have previous experience with that, it could throw off the machine's connections and the correlations it's derived. So therefore, having that geological information would allow it to account for those changes. So if we did include that data, then it probably would be able to handle that issue.
Okay, here's another question. To which factors the discrepancy of the predicted and actual thrust force could be attributed to?
Well, like the previous question mentioned, it's probably due to unexpected changes in geology. Since our system does not have geological data, it's possible that sudden changes in geological data could throw off its predictions and cause discrepancies like this.
Okay, another question. What is the usual output from the recurrent layer?
So I'm not sure. Okay, so essentially the idea behind the recurrent layer is that we don't really know what the input outputs of the hidden layers inside of the network is. The idea is that the weights and the system inside the recurrent layer will naturally adjust its weights to account for that. I guess what I can say is that the recurrent layer, the output it's giving would be the result of how the machine evaluated each of the inputs, and that information would be relevant to the next input. So ultimately, the only part that we can really interpret easily is the input and the output. The internal parts of the network, the hidden layers, that kind of information tends to be a little more difficult to parse.
Here's a follow-up question. If one thinks about the prediction of machine values, in this case, a machine in ground, how does this differentiate from classical predictive maintenance approaches, which also try to predict machine values?
Right, so predicting machine values with more traditional methods, I think that the key difference there is that in general, they will be more, the approach it's taking will be more static and clearly defined. So it will be dependent on a certain structure that has been defined for how it's going to predict, what weights is it going to apply, how is it going to, what factors is it going to include. The nature of the neural network and deep learning systems here is that by being able to take the previous time steps, it's also able to derive connections of which time steps are most important. It's also able to create its own prioritizations of which the most important factors are. For example, it could say that the previous time step isn't so important, but the ones 2-3 time steps ago are more important. That's not something that you could really manually set up in a more classical approach.
Okay. Is this model, when this model is applied to different TBM machines, does the sensitivity of the model change?
Well, we actually did only test this on the results of only one TBM, the Angeli TBM that the LA Metro was using. Now, I'm not sure that the accuracy would change depending on the machine. I guess that depends on how accurate the sensor readings of the machine are. But I would think that the bigger change would be dependent on the work site the machine is being used on, the geological conditions. The machine itself, I don't think, would cause much of a difference in the results.
Okay. Is there any advantage in using other machine learning regressors?
We have actually been considering using some other machine learning models to approach this problem. We've been considering using generative adversarial networks, which could be used to try and, what the idea is that we have one system that's creating results, like creating a possible output, and the other part of the system is trying to differentiate between that system and the reality. So in doing so, it's training the other system to try and mimic the reality as exactly as possible. That is something we're researching right now. We've also been considering using some new techniques like transformers to predict this. So there are other advantages, and that is something we're looking into.
Okay. And the last question is a two-part question from one of our attendees. At this point, can this method apply to a relatively small tunnel data and then later to a real tunnel data? And the part two is, what kind of sensors were on the TBM?
Right. So I think that is actually the key to the transfer learning thing. I think that is where it would be used. We use it in a small tunneling data. Perhaps we do some initial digging. And then if it's in similar geological conditions, then ultimately it's going to be basically the same correlations it's deriving. So I think those weights could absolutely be retrained or be reapplied from a small tunnel to a real tunnel, so long as they're in the similar geological conditions. Now, as for the sensors on the TBM, I think I have a couple of examples here. There we go. So yeah, the aqua articulation force, the thrust force, the advanced speed. We also had like the foam injection ratio, the internal pressures, the cutter head rotation speed, the what was it? The ratio between the soil and the, I think, the slurry collection rate. So overall, we were just using all of the mechanical sensors, all of them together, and we were only eliminating ones that were directly related to each other, like some of the sensors were actually being derived from one another, like if it had the quartile of some results compared to the total results, then we wouldn't use those together. Apart from that, we were using every single one of the mechanical sensors. The only sensors that we really did not have access to are geological data sensors, and I think that's tracking the soil composition, or like the front-facing sensor I showed earlier.
All right, thank you, Kabir, and also Dr. Pur Homayun for your presentation. I would like to go ahead and share the introduction slide for our next speaker. All right, our next speaker is Dr. Tamir Epel, who has recently completed his PhD in Civil and Environmental Engineering at the Colorado School of Mines. Tamir has joined Mott MacDonald in California as a tunnel engineer, and before starting his graduate studies in the US, he worked for 3 years as a tunnel designer in Israel, and he took part in the design of Road 6, sections 3 and 7 tunnels, and also led the design of several smaller tunneling projects. So with that, Dr. Epel, please go ahead and share your presentation.
Thank you, Reza. All right. Okay. So, thank you, Reza. I'll be presenting today on the examination of segmental lining loading for soft ground tunnels, design approaches versus actual behavior. This was part of my PhD research with my advisors, Dr. Mooney and Dr. Gutierrez, spoke earlier. And we'll start off talking about the analysis approaches used in tunnel design. So in tunnel design, we have several analysis approaches. First of all is the analytical solutions that are used for preliminary design, and also for checking and more validating the results we get from 2D plane strain analysis and 3D numerical analysis. That we'll find 2D in almost every project, and 3D in the more complex projects. And as I mentioned earlier, we have several design assumptions that we commonly use. First of all, segmental lining joints, ground behavior, elastoplastic, tunnel preconvergence, and construction process staging. Where in this study, we'll concentrate mostly on tunnel preconvergence and construction process staging. So, tunnel preconvergence is usually addressed in analytical and 2D numerical solutions, where tunnel preconvergence is the deformations that occur as the tunnel progresses. So in 2D analysis, we can only model the cross section, the 2D cross section. However, in real tunneling, we do have the 3D effects of the distance from the face. Farther ahead of the face, we have very little displacements and no displacements. And far behind the face, we have the maximum displacements. And somewhere in between, we install the lining. Where we install the lining, the more convergence that occurs, the lower the lining loads are, and the smaller the convergence that occurs, the higher the lining loads that are. This is, you can categorize this by two main approaches. The first is the wished into place method, where we assume no relaxation, no pre-convergence at all. So we're basically installing lining far ahead of the face, and the full magnitude of loads is taken by the lining. And in the convergent confinement method, we know the distance from the face where the lining is installed. We can calculate by LDPs the distance, the deformation that occurs at that distance, and relating that to the ground reaction curve, we can, knowing the displacement that occurs, we can calculate the lining loads. So the second assumption is about construction process assumptions. Talking about pressurized tunneling, EPB and slurry TBM tunneling, the main factors are the shield ground interface, face, chamber, shield, annulus pressures, and grout injection and time-dependent hardening of the grout, and pressurization of the grout material itself. So to look into these design aspects, we looked into the Northgate Link project in Seattle, where 5.6 kilometers of twin bore tunnels were excavated with 23 cross passages, and with these main characteristics of the main tunnels, and most importantly is the 10 centimeter gap between the shield and the excavation. The geology the project was excavated through is complex and highly variable interlaid glacial deposits, where in this cross section that we'll discuss in this study, the tunnels were excavated through cohesionless sand and gravel, and most importantly, from what we're taking from this project is the instrumentation and monitoring of the strain gauges in the segmental lining, where segmental lining strain gauges were installed in 17 cross passage locations. Here in this presentation, we'll talk about one cross section where 2 rings were instrumented. The rings were located at the second tunnel, so at the first tunnel that was excavated, no instrumentation was installed, only in the second tunnel. And in each ring, 3 strain gauges were installed, as you see here, with only the orientation of the segments changing according to the ring build. And in each segment, 2 strain gauges were installed, one in the intradose and one in the extradose, allowing us to analyze both thrust forces and bending moments. So to study these assumptions with the field data that we have available, for the first study included 2D numerical analysis using FLAC 3D, where the lining was modeled by linear elements with direct behavior of the joints using rotational stiffness, time-dependent grout stiffness. The ground was modeled using the hardening soil model. And the 2 assumptions that were studied in this part of the research was the wish into place assumption and the convergence confinement method, the pre-convergence, allowing for pre-convergence assumption. So with the wished into place assumption, after undisturbed conditions, we remove the tunnel material and install the lining. In the convergent confinement method, after undisturbed conditions, we remove the material, apply a radial stress, allowing for pre-convergence according to the convergent confinement calculations, and only then install the lining. So here, let's look at the results at tunnel 1 that is on the left before the second tunnel is excavated. Here on the left, we see the bending moments. On the right, we see the thrust forces. In blue is the wished into place results, and the red is the pre-convergence results, the convergence confinement method results, where important to know that in the first tunnel, no strain gauges were installed, only in the second tunnel. But first of all, let's talk about the forces that develop in the first tunnel, where we see a very significant difference between the wished into place and the pre-convergence method after the excavation of only the first tunnel, where the wished into place is significantly higher, both in thrust and in bending moments. And after the second tunnel is excavated, so now we have also the effects of the excavation of the second tunnel on the first tunnel, we see that the wished into place forces, both thrust and bending moments, are not affected significantly by the excavation of the second tunnel. However, the pre-convergent method there is a significant effect on the lining loads in the first tunnel as a result of the excavation of the first tunnel. We see here the increase in loading. So now let's look at the second tunnel that was excavated, the lining loads in the second tunnel, where we do have the instrumentation results, the field measurements, that are seen here by the points, these red points. And we see a much better prediction of the pre-convergence method compared to the wished into place method that overestimates the thrust force quite significantly. Well, in the bending moment, this is also seen. However, there is some higher bending moments in the compared to the pre-convergence prediction. So this brings us to the findings where the wished into place analysis overestimates the thrust force, in that the actual thrust force is about 30 to 50% less than the wished into place prediction. The actual low thrust force results in an unconservative bending moment, normal force, capacity envelope when using the wished into place analysis. Brings us up here, while the real results are closer to the envelope itself with higher bending moments and lower thrust forces. So this is important to have in mind, that despite that we perceive the wished into place method as more conservative due to the results that are higher, however, this concrete design aspect is deceiving. So now let's move on to the construction process assumptions, looking at the shield ground interface assumptions. So common assumption in 3D modeling is that the shield is in full contact with the ground. The TBM excavates, the excavation diameter is slightly larger than TBM shield, as I discussed earlier. In most projects, it's about 2-3 centimeters. In the Northgate Link project, as I mentioned, this is larger. And in the past, it was assumed that the ground converges onto the shield as in full contact with the shield. However, as part of the effort to reduce surface settlement, pressure behind the TBM shield plays a more important role. The pressurized material from the chamber fills the annual gap and supports the excavation boundary, the excavation itself, as it's pressurized also behind the shield. We can see this for the Northgate Link project. Here in the bottom figure, we see in blue is the chamber pressure measured at the top, and in red and green are the shield annulus pressures. Red is the front shield, green is the back shield, and this connectivity between all the measurements shows us the connectivity between them and the pressure supporting the excavation boundary. So with this, the main innovation in the flat 3D model developed for this part of the research is the simplification of the shield by annual shield pressure As you see here, in addition to modeling the face pressure, we also model the annulus shield pressure instead of modeling the physical shield itself. This process and incorporating also more complex structural time-dependent behaviors of the TBM modeling construction process itself, including the annulus grout pressure, segmental lining, the joints themselves, two-component grout time-dependent behavior, and so forth. This process is done both for the first tunnel on the left and the second tunnel on the right. So here, again, we're looking at the first tunnel that was excavated with no instrumentation installed. So before the second, only after the first tunnel is excavated, the results are shown by the dashed line here. And after the excavation of the second tunnel, we see the results in the solid line. And here we see the same results as we saw earlier, where we have a significant influence of the second tunnel. Now let's look at the second tunnel that was excavated, where two rings were, as we mentioned, two rings were instrumented. The first ring, ring A, in blue, and ring B, red. The second ring in red. Here we see there's the field measurements separated in red for ring B, blue in ring A. And as we see, there is a significant, numerical model predicts the ring B quite well. However, ring A is significantly underestimated by the numerical model, as the field measurements are about 30% higher than the ring B, and also a bit more than that from the predicted measurements. And for the bending moments, we see quite a good prediction, as we saw earlier as well, of the numerical model. This significant difference between ring A and ring B brought us to look into the TBM pressures itself, the measurements of the TBM pressures as the excavation was conducted. And you can see here on the bottom, in the darker areas are the excavation cycles, and in the white areas are the standstill due to ring build, where after ring A comes out of the shield, we see a significant pressure drop that occurred in the chamber. And this also occurred after ring B came out of the shield. So these pressure drops were also incorporated in the 3D model, where after ring A came out of the shield and was installed, the pressure drop. So here we see the vertical effective stresses on the top before pressure drop, and here after pressure drop, where the vertical effective stresses illustrate the radial stresses around the tunnel. And what we see is after the pressure drop, we have a decrease in the radial pressures around the shield itself as the pressure drop. And this pressure redistributes to the first ring that's installed, increasing the radial stress around the ring and increasing the thrust force taken by this ring, as you see here by the blue line. That is the prediction by the 3D numerical model incorporating the pressure drop. And we see a very good prediction of that. And also the prediction of the ring B also matches very well the field measurements as well. And we see very little influence on the bending moments. So the main conclusion from this part of the research is the importance of the shield annulus pressure on lining loads that is shown here by the pressure drops, the influence of the pressure drops on the lining loads. And while we usually think of the shield annulus pressure that is used to reduce surface elements, we see here also the influence of that shield annulus pressure on the lining loads. that is also important to incorporate and use in predictions as well. And this was also basis for the next part of this research that I won't present here today, but how important using these pressures also to predict lining loads, to calculate longitudinal displacement pressures, and so forth. So I think I finished quickly. So any questions? Now I hope it came all the way.
All right, thank you. I think this is a good time for questions and answers from the participants and attendees. All right, there's a question about the following. How did you correlate the hypothetical moduli of elasticity of the ground with the shield loadings?
Okay, so because I used the hardening soil model, so I used the hardening soil model to model the soil. I validated the hardening soil model using both triaxial tests from the field and pressure meter tests, and then this in the hardening soil model, the moduli is stress dependent, so it's stress and strain dependent. So that's what I used. Does that answer your question?
I believe so. I think the question was about the hypothetical moduli of elasticity, which was discussed there. Okay, so we are open for any additional questions for Dr. Hippel's presentation.
The injection pressure at the annulus gap was varied between each tunnel. So at the first tunnel, it was about 200 kPa, and at the second tunnel it was higher, was about 350 kPa, if I recall correctly. So, and also I think it wasn't investigated further, but we started investigating a different project. But the grout injection pressure in the Mohr Coulomb model, it will be more significant because the unloading reloading modulus is the same as the loading modulus. However, in the hardening soil model and in real soil behavior, the unloading reloading modulus is higher. Then the injection pressure has less influence also. So
there's another question. How did you model the joints?
Okay, so joints were modeled directly by rotational stiffness of each joint. Each joint by the Janssen model, we know the normal force at the joint and the bending moment range. We can give a rotational stiffness of the joint itself. So that's how the joints were modeled. Only the rotational stiffness itself. The translational stiffness, the XYZ were rigid in this case.
There's a question about potential ways to get more information about the methodology that was developed and implemented in your talk.
Yeah, I can send copies of our paper, and also we can share PDF copies of the presentation.
Perfect, thank you. We'll make sure to make those available to folks participating.
Yeah.
If either Dr. Pourhomayun or Kabir are on the line, there's a question. One of the attendees have asked, I would like to know if the shift change was considered or if it can be considered in the deep learning analysis.
So I would say that basically all of the different factors need to be accounted for. So yes, I think it probably could be accounted for in the analysis, but we'd probably have to select the features more carefully to account for that, to determine what exactly we're going for and what problems we're trying to solve. So the features would have to be selected differently.
How does the ground classification would impact, such as swelling soil or flowing soil?
How would it impact lining loads?
Yes.
So that is a different, that So that's a different analysis, I think. So for swelling soil, it's just a calculation of how much it swells after the lining is installed. So it actually doesn't have any relation to the convergent confinement method or also the pressure, because it's a completely different process that happens after the lining is installed and not related to that. So I think so. It's a different analysis by its own.
Okay. I think there is another question for you, Tamir. How was coupling in the ring joint modeled in 3D? To be more precise, the circumferential joint between neighboring rings is considered.
So that's a great question. So this is a problem I addressed more in cross passage design. So I have in my my thesis, I have a whole different aspect about cross passage design where this is more taken into consideration. Here, there is a very low frictional behavior between rings and with a very low connectivity and stiffness and frictional mechanism. However, this is also a different aspect to be looked at that depends on the normal forces, that the jacking forces of the TBM, and I looked more into that in aspects of cross passage design and not not in these twin tunnel problems, simple twin tunnels. So yeah.
Okay. All right, thank you. All right, at this point, I'd like to thank all the attendees and the 4 presenters for their time. Of course, these topics are of interest, and if you happen to have some additional questions that could be answered, please reach out to us. We had the email and contact information for the presenters that will be available in the recorded webinar presentation and recording file that will be available to you as well. But here, I like to just browse through the contacts as well. Like I said, we will make sure to have the recording of the webinar available to you. For those of you who are interested in receiving your professional degree over certificate, online certificate, please reach out to us at learn@mines.edu, and we have a procedure in place to issue you the online certificate with the cost of $15. And I would like to also encourage everyone to stay tuned and look for the upcoming webinars. Please visit our website at underground.mines.edu/UTC/UTI for some updates about the general ongoing research projects for the center and also the affiliated faculty and students involved with the existing projects. And that wraps up the webinar for today's offering, and we look forward to have you with us with our future webinars. Thanks, everyone.